Hello everyone, welcome to this tutorial. My name is Emerson Ahrari, I'm a Google Earth Engine specialist. In this tutorial I'm gonna show you one of the most useful drought indices. The drought index in this tutorial is a standardized soil moisture index, allowing us to understand about the soil moisture anomalies through the time. At the end of this tutorial, you will be able to produce the annual SSI index that shows soil moisture variations in different levels through the years. For example, we can understand which year received more moisture compared to the others. This tutorial is very useful for those of you who are interested in drought monitoring. There are a lot of drought monitoring tutorials on my YouTube channel, and this one could be a good complementary to get more understanding about the drought situation. Okay, if you want to learn this tutorial and if you want to learn how to do this procedure from scratch, follow this tutorial. So, first of all, go to the Colab environment and make a new notebook. As you can see, I'm doing this. The Colab environment is free of charge and publicly available for all of researchers, students, and also ordinary people in all around the world. In the first step, we need to install or import essential libraries into the Python for programming in this environment. So let's start with Earth Engine related libraries. Import Earth Engine, import GEE map, and install XEE. The XEE is one of the newest libraries developed by the Google community and allowing us to combine the X-array structure with the Google Earth Engine image collections format. That is really beneficial and extend our capabilities to apply machine learning techniques on the satellite data. Import XEE and then import X-array as XR. The X-array allowing us to actually use multi-dimensional format for the satellite data with the array structure that facilitates machine learning analysis. It's a complementary library for the XEE. We need both of these together to apply X-array structure on satellite data. And then other libraries like NumPy and Pandas should be installed or imported. Import NumPy as NP, import Pandas as PD, just like that. Let's click on connect first. The Colab is connecting to the server and then you can run the cell. Okay, you can see the cell is running and the executing count time actually showing here. XE is installing. Actually, the XE is not built-in available in the Colab environment. That's why we need to install it first. Okay. After installation, after you see the message installing collected package and successfully installed, then you can clear the outputs just like this. In the next step, we need to establish a connection between Earth Engine and Colab environment. Okay, let's do it using EE capabilities. Let's start with authentication and initialize. Initialize Google Earth Engine account. Start with the project name. The project name refers to Google Earth Engine account ID. Go to the code editor environment. Upper right, there is a button that shows your account information. Go to project info and your own cloud project is available here. This is mine, and also you can find yours through this address. Another parameter or another argument is OPTURL. If you go to the net, or if you browse on the net and search about Google Earth Engine and XEE, you will find a GitHub page. According to this address, there is a detailed instruction about XEE library, how to open the satellite data, and also how to initialize it. The OPT URL already addressed here, and just I'm gonna copy the URL into my code, just like this. And let's run. Now, Colab asking permission to access to the Earth Engine account. Click on your account and then continue. The permission granted by you or by the user. From now on, we can use Earth Engine capabilities such as data catalog and functions in the Python environment. And this is an incredible opportunity because we have a wide range of capabilities to deal with the satellite data, whether it is in Python built-in or in the Earth Engine available. So, in the next step, we need to identify or we need to define the region of the interest in the first step. Make a new variable map sets to. So here we from GEE map call the map function. Define a base map based on satellite view. Let's print the map. You will have a user interface in which you can define your region of interest easily. I'm gonna select my own country, Iran, in this tutorial. Through rectangle tools available here, draw your region of interest, just like that. This tutorial is not limited to a specific location or a specific kind of satellite data. You can use this tutorial for all soil moisture data and also for all locations in all around the world. So now we need to have the rectangle as a shapefile in the code to actually bound the region of interest to that. So to do this, create a new variable, for example ROI, and then from map select the last feature that is defined, convert it to geometry same time. So the ROI created. In the next step, we need to call smap soil moisture data. Go to the code editor environment, through the search places on dataset, type smap data. Here you can see the smap product is available with 9 km resolution and daily frequency. Two products available, version 5 and version 6. Both of them are same, but they are different in the temporal extent. Version 5 actually ranges from 2015 to 2023. That's my target collection for this tutorial. So now as you can see here, a new variable smap created. Sets to, make a parenthesis like this and paste the collection snippet. Then select the target band here. So what is the target band? Go to the data characteristic and here there is a band information. Spatial resolution is 9 km and the target band is soil moisture AM. So that's my target band here, soil moisture AM, selected like this. And then define temporal or date filter date, temporal period. Make two variables such as time start and time end to filter your data based on. Make another cell and define time start like this, Earth Engine.date from 2016, for example, until 2024. That's date 2024. Regarding to the dataset availability, we can have access to the data for this period of time. Okay. In the next step, so as you can see, the time start and time end created. Let's print the smap, run the smap, and print to see how many smap satellite data is available for this period of time. Here we have the daily soil moisture data set, and more than around 3,000 satellite data available for this period of time. I need to convert them to the monthly frequency first, or a monthly interval. So it is very easy and fast in the Earth Engine. Just a couple of lines coding is necessary. First of all, we need to calculate the temporal difference between the time end and time start here. Time end, that's difference, time start, and based on months. So how many months do we have between time start and time end? Round it. Let's get a print from the time difference. 60 months available, or is our duration between time start and time end. Now I need to make a list based on Earth Engine. That's list, that's sequence. The list is starting from 0 to the number defined or calculated by time difference. As we are starting from 0, we need to subtract by 1. So with 1 frequency. In the next step, print time list, and you can see we have a list of values from 0 to 95, but we need to replace this value with the dates. So now make a loop structure like this. That's map. Lambda is a function. The function input is x. From time start already defined here. We want to go advance based on x interval and months units. Let's run again. A new list created and replaced with dates from early to the late. So there it is, a list of dates created. In the next step, I need to calculate the average of soil moisture for each month. Make a new function here. A new function created, the monthly function. The function including 2 arguments. The first is the date list, already created, and the next one is the target image collection. Okay, now we need to define a new start and end date for each month separately. So Earth Engine.date. The start date already defined through the list, ee.date, like this, and end date equals to, from start date, go advance again with 1 month interval. Okay, for each start date here, 1 end date created. Now we have the start and end of each month. Let's filter the data or image collection based on each month's dates. Then calculate the average. The function returning the average image or monthly average with a new system time start. This will be a start date with millisecond format, just like this. Okay, now we need to apply monthly function on smap data. Smap monthly, a new variable created, sets to Earth Engine image collection. Bring whole of the process into an image collection. So bring the list, and now on the list of the dates, list of the start dates, I'm gonna apply the monthly function. So lambda is a function. For each date, we want to do this. Each date considered as a x, and monthly function applying on each date and SMAP image collection. Let's run. SMAP monthly is ready. So 96 SMAP images available. There it is. So in the next step, we need to go to X-array structure for the further analysis. You can see that here we utilized Earth Engine capabilities to prepare the satellite data for the rest of the work. So from now on, I need to convert image collection format. As you can see, we have one image collection into the X-array structure because in there are various algorithms allowing me to easier calculate the rest of the processing. So make a dataset from X-array library called open dataset. The input image is mapped monthly. Engine sets to EE, CRS coordinate system, EPSG 4326. This is a unique ID for WGS84 and is same for all around the world. The scale sets to, for example, 0.1 or 10 kilometer. Because the spatial resolution is 9 kilometer, now actually I rounded up to 10 kilometer. So the scale is based on the degree. 1 degree equals to 100 kilometer, but the here scale 0.1 means 10 kilometer. So the geometry or the region of interest sets to the ROI or the region of interest or the drawing area or rectangle area already drawn by drawing tools. Let's run the data set, and after a few moments the monthly soil moisture data is ready. So there it is. From image collection dataset converted into an image into a array structure or using X-array multi-dimensional format. Here we have different dimensions: time, longitude, and latitude, and also the data variables actually explaining soil moisture over spatial and temporal variations. So in the next step, I'm gonna show you how to calculate this standardized soil moisture index. The SSI or standardized soil moisture index, somebody says SSI or sometimes we call it SSMI. So anyway, the index equals to a division between soil moisture for each date minus to the soil moisture average over to soil moisture standard deviation for the long term. This is the equation. For this equation, the monthly soil moisture already prepared, we need to calculate the average and a standard deviation. Make a new cell structure, and here we need ds average sets to ds.min. We want to get average through the time. That's why the dim should be sets to time, not over a spatial dimension. ds min is calculating, and you can see executing time. So it typically takes less than 1 minute, sometimes less and sometimes more, depends on the volume and size of the input data. So before process is over, I should mention that if you have any problem or any challenge regarding this tutorial, you can find the code example below this video on my YouTube channel, and that will be help you to find the potential errors or potential problem in the coding environment. So as you can see, the average image created, the average soil moisture image created after 41 seconds. Okay, ds average, here it is. no longer time is available, and only longitude and latitude and data variable remained. Let's make a plot to see how soil moisture average looks like in the study area. So VS min, the soil moisture band name, just like this, and make a plot. So the plot is x-axis sets to longitude, y-axis sets to latitude, and the next is the robust sets to true to avoid outlier impacts on visualization. Let's run, and here it is. You can see this annual or average soil moisture map for Iran. As you can see, uh, where we have actually significant variations, especially in this country. As you can see, in the northern Iran and also the southwest of country, you can see very high soil moisture values. That's because of the agricultural activities and water resources and climatological condition in this area. But the rest of the country, as you can see, received very low soil moisture level. So, and here you can understand about the spatial pattern of soil moisture variation in this area. So, in the next step, we need to calculate the standard deviation through the time. A new variable dsstd created and sets to ds.std, just like this, dimension through the time. We want to calculate the standard deviation through the time. Hopefully it's calculated really fast and quickly. So let's make a plot from the standard deviation and see how actually soil moisture varies from one location to another one. Again, x sets to longitude, y sets to latitude, and here robust sets to true, just like this. And you can see the actually the soil moisture fluctuations over the last years. In some areas with higher values, we had actually higher fluctuations, and regions with the lower values referring to lower fluctuations in terms of the soil moisture in this area. That could actually highly affected by the precipitation pattern and climatological condition. Okay, back to the equation. As you remember, this is the equation for standardized soil moisture index. Okay, now we can apply this equation really easy without any challenge. Okay, SSI sets to already the monthly soil moisture calculated. The DS minus DS average over DS standard deviation. Let's run and print the SSI. So as you can see, the SSI calculated, and now we can make a print for one specific year, for example. So here, for example, I'm gonna make a subset for a single or particular year. So SSI dot select time sets to, from SSI select go and select the time dimension dot dt dot year. So now I'm gonna select a year, a specific year, for example 2019. So could be considered in this step. Print the sub. As you can see, 12 SSI image available for 2019. So let's make a plot, a multi-temporal plot that's showing monthly SSI variation over this country. So SSI plot from a subset make a plot. Select the variable soil moisture, make a plot. X sets to longitude, Y sets to latitude, col sets to time because it is a multi-dimensional format, and call wrap, it means how many maps per row we need. For example, 4, robust, true. And the next parameter is, for example, could be the color palette or anything else. So let's run and see the result. So as you can see, we have a map, a monthly map about the SSI that shows the soil moisture variation through the time. As you can see here, the red areas showing higher soil moisture and the blue areas showing the lower soil moisture. So as you can see here, during the winter time, and also we received a very actually very high soil moisture in the whole of the country because of the heavy precipitation, and you can see its impact even lasted during the summertime, and also there are some hot spots, soil moisture spots even detected afterward because of the water actually bodies after precipitation or something else. So here that could give you a lot of information about the precipitation impact on the soil moisture variation through the time. So in the next step, I'm gonna show you how to make an annual plot and see how the temperature, how the soil moisture varies in this area. Or even I can even select a point on a map and see how much or how evapotranspiration changes over this area. For example, if you go to the code editor environment, it is really easy to get the precipitation soil moisture value. For example, in the southwest of Iran, in the north of Persian Gulf here, you can see we have actually a spot of agricultural activities here. And now I'm gonna see the moisture variation in this region. For example, I'm selecting a point here and easily you can find its coordinates. So let's actually find this coordinate on SSI map and see how the temperature varies from one time to another, how the SSI varies from one time to another time. So the SSI, let's make another subset. This time it is a point. So from the SSI image, I'm gonna select a point based on longitude and latitude. So the longitude is the first value, just copy and paste it. The next is the latitude, copy and paste it into the code. So there it is. And the method find the nearest point to this coordinate. Let's run, and here it is. We have actually the X array structure, but this time only actually the values. We have no longer longitude and latitude is available. Only the time is matter here. So we can all even convert it into the data frame. For example, here, make a new data frame, convert the point to a data frame. It is even easier to understand and for the rest of the processing. Here you can see time, latitude and longitude is available. We can skip the lat or long because they don't change through the time. And here so let me to select the soil moisture. Here it is, the soil moisture AM is a target band and time is indexed already. So here we have two columns, finally time and soil moisture. Let's make a plot, really easy, just like this. And here you can see the soil moisture variation based on SSI value. The SSI ranges from minus to positive, as I mentioned earlier. The negative values shows a low soil moisture compared to the long-term average, and positive values showing higher soil moisture compared to long-term average. This is very interesting things, and for example here you can see compared to the long-term analysis, the soil moisture level increased a lot in this period of time in 2019, and even it is comparable here for the selected point with the previous year and the years after. You can see it's really interesting. And now in the next step, I'm gonna show you how to make an average SSI map for each year. Then you can get a better insight about the years that are a little bit wet or dry, and you want to see how actually drought condition going on in your region of interest. So SSI with annual format. Let's start SSI dot resample to the annual format, temporal dimension to annual, and calculate the average through the time. Let's run, and after a few moments SSI annual is ready. Here it is. This is SSI annual, and you can see we have 8 years a soil moisture with annual frequency. uh, Actually it is the SSI, not soil moisture. Sorry if I say the soil moisture, I mean it is SSI. So let's make a print SSI annual dot select the soil moisture and make a plot like this. Again, X longitude and Y latitude, robust true, robust true, and the next one is the temporal dimension time called wrap. I need to have 4 image per row, and the next one should be color map or something else. Let's run to see what else needed. So here you can see the annual SSI values for the region of interest, and here easily understandable which years actually could be addressed as a wet year and which years could be addressed as, for example, dry years. For example, 2016 and 2017 actually were really dry with the lowest soil moisture compared to 2019 and 2020. Specifically, these 2 years and several flood actually happened in different regions in Iran, specifically in the northern side and also in the southwest, and also it was horrible and caused a lot of damages to the people and resources in this area. So, and such kind of mapping actually could give us a lot of information about the soil moisture and the phenomena or natural hazards that could be related to the soil moisture for these studies. Okay, now I'm gonna show you how to modify the output map. Sometimes you don't need the latitude or longitude because maybe it is addressed in your study area definition. If you want to produce the result for the results visualization, most of the time lat or long should be removed. So that's the first question mostly people ask. Let me show you how to do this for the whole of the plots. Doing this process is really easy, just we need to a little bit actually understand about the loop structure. For example, I'm gonna make a loop. Before making a loop, it is better to import the matplotlib. I forgot to make the matplotlib in the first step. Import the matplotlib. This library is the essential library in Python for plotting and plotting tools and techniques. So Let's make a loop structure because we have we have a multiple plots in a same sheet. So here for x, for example, let's make a variable for this plot. This is SSI plot. SSI plot sets to this for x in SSI plot dot axis dot flat. Okay, now we can remove the labels such as lat or line. So for x dot set y label sets to empty, x dot set x label sets to empty. Run and you can see the label's gone. So now we need to remove the ticks, numbers around the plots. X dot set x ticks for longitude and x dot set y ticks for latitudes. Let's run and you can see the ticks values also gone. In the next step, we need to increase the size of the titles because always reviewers asking researchers to increase the font size easily readable for readers. So x.title.set font size. For example, the font size could be 15. Let's run and you can see the map with the bigger font size. And also we need, or maybe sometimes you need to do some modifications regarding to the color bar. Let's select the color bar as a variable here. Plot C bar sets to SSI plot dot C bar. Okay, now plot C bar dot x dot tick params. We want to increase the label size to 15 for the numbers. You can see the numbers in the plot increased. Then we need to set a label for the color plot. Plot C bar again, set label. The new name is Standardized Soil Moisture Index, like this, SSI or SSMI, and the font size should be 15. Let's run and you can see the plot is updated. Okay, now we want to get export with the high quality plt.savefig. So the plot name is, for example, SSI annual frequency with PNG format. DPI.per-inch 360 typically offers a good quality. BB box inches guarantee all elements in the map locating into a single sheet should be tight. So go to the local file here and SSI annual is ready. Let's download and save it into your system. SSI annual is created for Iran and you can see this is a very high quality map and offering valuable information for the drought monitoring in your region of interest. I hope you liked this tutorial as much as I did and I asking you to share this tutorial with other remote sensing learners in all around the world. Thank you for the attention.